The Roman concrete. In 1980, while inspecting the ruins of an ancient harbor off the coast of Baiae, a team of Italian marine archaeologists made a strange discovery. Submerged under more than 30 feet of salt water stood a massive breakwater wall that had resisted the sea for nearly 2,000 years. Unlike modern concrete, which corrodes and disintegrates after a few decades in marine conditions, this structure was intact, its seams sealed tight, its composition hardened beyond expectation. The wall was built by the Romans, and its secret had remained buried just as deep as the ruins themselves. What puzzled scientists was not just its longevity, but the fact that it had grown stronger over time. The material, now known as Roman concrete, or opus caementicum, is unlike any modern equivalent. While today's concrete relies heavily on Portland cement, the Roman mix used a volcanic ash called pozzolana, combined with lime and seawater. Over time, this mixture forms a rare mineral called aluminum tobermarite, which strengthens the structure the more it is exposed to salt water. In other words, Roman concrete thrives where modern concrete fails. Core samples extracted from Roman ports such as Caesarea and Cosa have shown microscopic crystalline patterns that modern industrial processes cannot replicate, not even with today's advanced metallurgy or chemical engineering. By the early 2000s, multiple labs had tried to reverse engineer the formula. A 2017 study published in American Mineralogist confirmed that the unique durability came from interactions between volcanic material and seawater, forming interlocking mineral structures. But despite understanding this in theory, attempts to reproduce it on a commercial scale failed. The ash used by the Romans was sourced from specific volcanoes near the Bay of Naples, material that is geochemically distinct and nearly impossible to substitute. Even if the mineral balance could be mimicked, the Romans' centuries-long method of slow curing and underwater setting defied all modern timelines and construction economics. When news of these findings surfaced, further studies were abruptly halted. Industrial concrete conglomerates quietly distanced themselves from research projects associated with Roman construction methods. One of the principal investigators at a U.S. Department of Energy-funded lab was reassigned before publishing his full results. Documents filed under joint research agreements with European institutes vanished from public databases. According to whistleblower accounts, at least one attempt to apply for funding to revive ancient concrete methods was explicitly denied for being non-commercially viable and disruptive to existing infrastructure markets. Yet the implications remain staggering. If Roman concrete was used in modern dams, bridges, and coastal defenses, it could outlast current designs by centuries, possibly saving trillions in repair costs and environmental damage. But, more disturbingly, its suppression suggests that our built environment is deliberately kept fragile. Why would humanity abandon a superior material for one that fails within decades? What industry benefits from such obsolescence? In 2022, a satellite mapping project over the submerged parts of ancient Ostia revealed dozens of intact Roman concrete structures under the seafloor, still withstanding waves after 2 millennia. These relics are now off-limits to public dives, citing marine hazard protection zones. But if these structures are truly stronger than steel and untouched by time, then the very foundation of our modern construction industry is built on sand. The Damascus Steel. In 1837, during a British expedition in India's Hyderabad region, a Scottish officer named James Wilkinson acquired a curved sword from a local nobleman. Unlike any blade he had ever seen, it shimmered with a flowing pattern like liquid smoke trapped in metal. The weapon could slice through rifle barrels without chipping and bend nearly 90 degrees without breaking. Though its age was uncertain, local legend claimed it was forged centuries earlier, using a technique now forgotten. The officer sent it to London for analysis. Metallurgists marveled at its flexibility, strength, and beauty. But no one could explain how it had been made. That sword was an authentic artifact of Damascus steel, and its mystery continues to baffle scientists to this day. Damascus steel, known historically as Wootz, originated in India and spread through the Middle East by the 3rd century CE. These blades were legendary in the Islamic world and feared during the Crusades. Their signature feature was the damask pattern, intricate waves and swirls etched into the blade, not from decoration, but from within the metal itself. These patterns were the result of carbon nanotubes and carbide structures formed during the forging process, giving the steel its unparalleled strength and resilience. But modern metallurgists cannot replicate these microstructures with any consistency despite using electron microscopes, laser cutters, and high-carbon alloys. The original production method involved smelting iron ore with plant-based materials in sealed crucibles, a low-oxygen environment that allowed precise carbon absorption. This created ingots of ultra-pure steel, which were then repeatedly heated, hammered, and cooled using a rhythm that remains unknown. The slightest deviation in temperature, humidity, or forging time ruined the process. Equally enigmatic was the source of the raw materials. Some scholars believe the ores used contained traces of vanadium and molybdenum, naturally present in certain mines in southern India, which are now depleted or geologically altered. By the 18th century, true Damascus steel had vanished from production. European attempts to reproduce it, even with captured blades as references, failed consistently. Modern recreations using powdered metallurgy or acid etching can mimic the surface appearance but lack the internal latticework and mechanical properties of the originals. In 2006, a German research team identified carbon nanotubes in authentic Damascus samples, a nanostructure only recognized in science a few decades ago. But they could not reproduce them in a laboratory without artificial environments. How did ancient smiths, without microscopes or theoretical chemistry, create such advanced material at scale? Some believe the technique was deliberately lost. As colonial powers suppressed indigenous technologies and monopolized metallurgy, the oral traditions of Wootz forging were disrupted. The last known master forgers either died without apprentices or were co-opted into colonial armies, forced to adopt European steel standards. Others point to the destruction of trade routes and the decline of specific guilds following the British conquest of Mysore, effectively cutting off knowledge transmission. Few written records exist, and those that remain are vague or metaphorical, referring to breathing flames and singing iron rather than measurable data. If the real process of making Damascus steel could be revived, it would revolutionize modern weaponry, aerospace materials, and surgical instruments. The ability to forge steel at ambient temperatures with embedded nanostructures would render many modern factories obsolete. Is that why no serious funding exists for Wootz revival projects? Has something, or someone, ensured this knowledge stays buried? In 2019, a Damascus blade in a private museum in Istanbul was scanned with magnetic resonance imaging. The results showed anomalies in the metal's internal magnetic field, forming organized spirals not seen in any known alloy. No explanation was offered. The museum has since restricted access to the artifact. If Damascus steel truly embodies a lost science of molecular engineering, then its disappearance may not be accidental. The Orichalcum Alloy. In 2015, a team of marine archaeologists working near the Sicilian coast stumbled upon the wreck of a Greek cargo ship lying 10 feet beneath the waves, just off the ancient port city of Gela. Among the debris scattered on the seafloor were 39 gleaming ingots unlike anything they had seen. Though they had been submerged for more than 2,600 years, the bars retained a bright golden red luster that seemed immune to corrosion. Initial analysis suggests these were not gold, not copper, and not bronze, but a strange blend of metals with no known modern equivalent. The team had recovered what some now believe to be the lost metal of Atlantis, Orichalcum. Mentioned in Plato's Critias, Orichalcum was described as the second most precious metal in Atlantis after gold, used to adorn the city's inner sanctums and even the temple to Poseidon. For centuries, historians dismissed it as allegorical, until those 39 ingots surfaced. Laboratory tests revealed that the bars were made from a complex alloy of copper, zinc, nickel, lead, and trace amounts of rare earth metals. But what puzzled researchers most was not just the composition, but the purity and balance of the elements. The alloy did not match any historical recipe for brass or bronze. Its sheen, density, and spectral fingerprint were entirely unique. Modern metallurgy can combine metals in precise ratios, but the Gela ingots displayed microstructures that suggested an unusually slow cooling process and a series of chemical reactions under tightly controlled heat, something nearly impossible to achieve with the furnaces known in the 6th century BCE. Moreover, the materials in the alloy came from sources scattered across the Mediterranean and even sub-Saharan Africa, implying a trading network and technical knowledge well beyond what history credits to the Greeks of that era. How could a civilization that predated the Roman Empire create a material so advanced that we still cannot duplicate it today? Shortly after the discovery, access to the shipwreck was quietly restricted by the Italian Ministry of Culture. Independent researchers and private labs were denied further samples. The ingots were transferred to a state facility for preservation, and updates on the analysis abruptly stopped. One of the metallurgy experts involved in the original investigation left his university post without explanation, and his publications on the subject were taken offline. Some whispered that Orichalcum's rediscovery posed a threat to official timelines of metallurgy, or worse, that the alloy held industrial properties yet to be revealed. What makes Orichalcum so dangerous? Beyond its visual appeal, researchers suspect the metal exhibits unusual conductive properties. A brief electromagnetic test performed during initial analysis revealed irregular resistance patterns, hinting at possible use in energy transmission or signal shielding, properties highly sought after in aerospace and military industries. Could this be why further testing was halted? If so, then Orichalcum is not merely a relic. It may be a technology. In 2021, a leaked report from a defense contractor mentioned experimental alloys being benchmarked against historical samples of uncertain origin, including one labeled O.C. Gela. The contractor refused to comment, and the document vanished after a copyright claim. No further mentions of Orichalcum have appeared in mainstream science publications since. If the Gela ingots truly represent a forgotten science of material fusion, one capable of resisting time, salt water, and even electromagnetic interference, then the boundaries of what ancient civilizations knew may be far wider than we are allowed to believe. The Mesopotamian Lenses. In 1850, during the excavation of the ancient Assyrian city of Nimrud in northern Iraq, British archaeologist Austen Henry Layard unearthed a peculiar object buried within the ruins of a temple. It was a small, oval-shaped piece of rock crystal, perfectly smooth, with a convex curvature and an uncanny clarity. At first dismissed as a decorative item, further study revealed it was ground and polished to optical precision, functioning exactly like a modern magnifying lens. Layard had unknowingly rediscovered what is now called the Nimrud lens, and with it, one of the oldest optical devices ever found. The lens, dated to approximately 750 BCE, is carved from natural quartz and measures about 1.6 inches in diameter. It produces 2x to 3x magnification and exhibits an intentional biconvex shape, something that requires not just craftsmanship, but knowledge of how light behaves when refracted. Yet this was not an isolated case. Since the discovery of the Nimrud lens, similar polished crystals have been unearthed across Mesopotamian, Sumerian, and Babylonian sites, often dismissed as jewelry or ritual objects. But under closer inspection, many of these artifacts show optical properties too precise to be accidental. In 2007, researchers at the University of Geneva re-examined 13 such lenses using laser interferometry and found that several match the curvature needed for controlled focal lengths. These findings suggest not only an understanding of lens making, but also possible applications in astronomy, precision carving, or even surgery. This raises a difficult question. How did civilizations over 2,700 years ago achieve a level of optical engineering thought to belong only to the Renaissance? Conventional history holds that lens making for visual enhancement began with the Greeks, and optical instruments like the telescope didn't appear until the 17th century. Yet, cuneiform tablets from the same era as the Nimrud lens contain star charts with surprising accuracy, including depictions of planetary motion and stellar anomalies invisible to the naked eye. Could Mesopotamian astronomers have used lenses to observe the skies? If so, it would overturn centuries of assumptions about the origins of science. Despite their potential significance, most of these lenses remain locked away in museum vaults or misclassified in artifact archives. Requests to reclassify them as scientific instruments rather than religious items have been repeatedly denied. In 2012, a visiting optics expert from a German research institute was barred from scanning a collection of Mesopotamian crystals at the British Museum, after raising questions about their possible magnification properties. The official reason cited was preservation concerns, but no such restriction existed for other quartz-based artifacts. What might these ancient lenses have been used for? Some theories suggest the Mesopotamians could engrave microscopic inscriptions or construct precision tools. Others speculate they were components of a larger optical device now lost to time. A few radical voices even propose they were used in communication, focusing light over long distances like primitive lasers. A claim dismissed by mainstream academia, but never experimentally disproven. Satellite imagery of desert dig sites in modern Iraq shows several patterns of stone alignment resembling sundials or optical arrays. These areas have since been declared restricted zones by government and military authorities, citing heritage protection, though no public research has occurred there in over a decade. If the Mesopotamian lenses represent a suppressed chapter in the history of optics, then humanity's timeline of discovery may not be linear at all. It may be cyclical, with knowledge gained, lost, and quietly buried under sand and secrecy. The Egyptian antibacterial gold powder. In 1924, while cataloging artifacts from the tomb of High Priest Ankh-Kor, archaeologists at Saqqara encountered a layer of gold dust covering the inner wrappings of his mummified body. At first, it was assumed to be symbolic, part of the wealth and divine association often attributed to Egyptian burial practices. But under microscopic analysis at the Cairo Museum's early conservation lab, something unexpected emerged. The particles were far finer than any known ground metal, nearly uniform in size, and displayed properties that defied the limitations of ancient metallurgy. What began as a decorative feature soon revealed signs of something far more sophisticated and troubling. Samples of the gold dust were later reanalyzed in the 1990s using scanning electron microscopes at the University of Tübingen in Germany. The results showed nanoscopic flakes of gold, each less than 50 nanometers in diameter, with a protective coating of an unidentified organic compound. Even more perplexing, the gold particles exhibited broad-spectrum antibacterial properties. When tested against colonies of E. coli and Staphylococcus aureus, the flakes eliminated over 99% of bacteria within minutes. Unlike modern antibiotics, the reaction appeared to be purely mechanical, likely a result of how the particles punctured cell membranes. In essence, the powder functioned as an ancient biocide. Modern nanotechnology has only recently begun to explore gold's potential in medical applications. Yet here was a funerary treatment from nearly 2,600 years ago, achieving the same effect with a level of particle control that modern machines still struggle to replicate. Current gold nanoparticle synthesis requires centrifuges, chemical baths, and electronic monitoring. The ancient Egyptians had none of these. So, how did they achieve a uniform particle size distribution at the nanoscale? Some believe the secret lies in biological processes lost to time. Pollen from rare desert plants was found within the wrappings, suggesting an organic origin for the binding compound. Could Egyptian embalmers have used plant enzymes to break down gold into nanoform and then stabilized it with proteins or resins? No formula for this process has been recovered. No known texts describe it. But the chemical signatures suggest a reaction that modern science cannot reproduce outside lab conditions. After the initial discovery, the powder samples were quietly removed from public display. Official museum records now list them as gilded dust, grouped with ritual cosmetic items. Attempts to acquire samples for further study have been denied on the grounds of artifact preservation. In 2001, a prominent biochemist at a Swiss lab claimed he had recreated a similar effect using ancient recipes extracted from the Ebers papyrus. Before he could publish his findings, his lab's funding was pulled and his research shuttered. No explanation was given. The only remaining references to his work exist as citations in obscure chemical journals, without full text access. If the ancient Egyptians had mastered antimicrobial technology at the nanoscale, and used it not just for embalming, but perhaps for medicine, then this knowledge could have changed the course of modern infection control. Instead, it was buried, sealed in resin, and dismissed as religious excess. The last time the Ankh-Kor wrappings were viewed under laboratory conditions was in 2015 during a short-lived conservation program funded by the Egyptian Ministry of Antiquities. The program was terminated midway through its first phase. All lab notes remain classified. If ancient gold powder could kill bacteria without chemicals, without resistance, and without decay, then the loss of that knowledge may have cost us more than we know. The Greek fire resin. In 678 CE, during a critical naval engagement off the coast of Constantinople, the Byzantine navy unleashed a weapon that terrified the Arab fleet into chaos. Jets of fire burst forth from the prows of Byzantine ships, clinging to the surface of the water, igniting anything it touched. Witnesses reported that the flames could not be extinguished by water, and would even spread more violently if one attempted to douse them. The Arabs called it naft. The Byzantines called it liquid fire, but history remembers it by a more ominous name, Greek fire. And the formula behind it remains one of the most closely guarded and completely lost military secrets of the ancient world. The deployment of Greek fire was described by multiple chroniclers over the next centuries, from Theophanes the Confessor to Anna Komnene. Yet none could identify its exact ingredients. It was reportedly delivered through siphon-like devices mounted on warships, suggesting a pressurized system far ahead of its time. The substance itself stuck to human skin, burned underwater, and resisted smothering, behaving more like a living organism than a conventional chemical compound. Modern pyrotechnics have failed to replicate these effects using known medieval ingredients. Several theories have been proposed. Combinations of quicklime, naphtha, resin, sulfur, and bitumen. But in all modern reconstructions, the key properties, water resistance, adhesive spread, sustained burn, remain elusive. A breakthrough in 2003 by a team at the University of Thessaloniki came close. They managed to produce a gel-like flammable resin that burned atop water surfaces. However, it required stabilizers and synthetics unavailable before the industrial age. The ancient version, whatever it was, did not rely on refined petroleum or modern chemistry. It worked in battlefield conditions using materials and techniques still unknown. The original formula was allegedly held only by a single guild within Constantinople, passed down through bloodlines and closely guarded under imperial decree. Anyone attempting to reveal it faced execution. When the Fourth Crusade sacked the city in 1204, the chain of transmission was broken. All records, if they ever existed, were lost in the fires that consumed the imperial archives. What remains are only fragments, mentions of sea oil, wild flame, and burning stone, scattered across conflicting manuscripts, many of which were rewritten or censored in later centuries. In the 1970s, declassified reports from a NATO naval lab in Naples revealed tests on ancient incendiary techniques. One entry mentioned an organic phosphorus derivative extracted from historical sources, which reportedly ignited on contact with seawater. The trial was halted due to safety concerns. The substance, labeled GFR7, was never identified. Some believe the military has been attempting to reverse engineer Greek fire for decades. Not as a weapon of war, but as a material science breakthrough, a fire-resistant, water-repellent compound for aerospace or underwater applications. Access to certain Byzantine-era shipwrecks in the Aegean Sea, particularly near the island of Chios, has been restricted since 2011. Officially, it's for conservation. Unofficially, dive teams report the presence of sealed amphorae containing tar-like residues, but none have been recovered for public study. One independent archaeologist who reported such a find was later barred from renewing excavation permits. If Greek fire was more than just a weapon, if it was a chemical technology capable of defying natural elements, then its loss marks not just the fall of an empire, but the erasure of a scientific marvel, a material that ignored the rules of water, oxygen, and heat, and that no one, not even modern chemists with satellite labs and spectrometers, can fully decode. The Wootz steel of India. In 1795, a shipment of swords arrived at the Royal Arsenal in London, gifted by a princely state in southern India. One of them, a curved blade with swirling patterns embedded in its metal, caught the attention of metallurgists. When tested, it sliced cleanly through European steel without losing its edge. It bent without snapping, and under the flicker of torchlight, its surface shimmered like water rippling under moonlight. This was no ordinary sword. It was forged from Wootz steel, a metallurgical enigma that had once armed warriors from Persia to Southeast Asia. Despite centuries of admiration, the secret of Wootz vanished by the mid-1800s, and modern science has never managed to bring it back. Wootz steel, the precursor to the more famous Damascus steel, originated in India as early as the 3rd century BCE. It was renowned for its purity, strength, and the signature watering pattern caused by the alignment of carbon nanotubes and carbide, microstructures. Unlike cast or wrought iron, Wootz was made in sealed crucibles where iron was melted with carbon-rich organic materials, like dried leaves or wood chips, in a low-oxygen environment. This process created ingots of ultra-high carbon steel with a unique internal architecture that gave the metal its legendary performance. When modern researchers attempted to reproduce Wootz, they found the process astonishingly delicate. Even a slight change in temperature or atmosphere during forging altered the carbon distribution, resulting in brittle or uneven blades. Despite having access to electron microscopes, thermal cameras, and automated kilns, metallurgists failed to consistently generate the flowing patterns or mechanical properties of original Wootz. In a 2006 study, researchers identified nanowires of iron carbide embedded in authentic Wootz samples, structures that only form under very narrow thermal conditions, likely discovered by ancient smiths through generations of trial and error. The source of the iron ore also plays a critical role. Historical records suggest that mines in Tamil Nadu and Telangana contained unique trace elements like vanadium and molybdenum. These micro-additives, combined with the right carbon source and firing conditions, may have been crucial to the alloy's properties. But those mines are now depleted, and even when ore with similar composition is located, the results fall short. The specific trees and plants used in the crucible process may also be extinct, eliminating another key variable from replication efforts. By the time British colonial policies forced the closure of native Indian arms industries in the 19th century, the Wootz tradition was already in decline. The oral transmission of forging knowledge, passed down through blacksmith lineages, was disrupted. Guilds were disbanded. Local expertise was labeled primitive and replaced by European ironworking techniques. With no written manuals, the knowledge dissolved within a generation. In recent decades, several defense and materials science institutions have quietly explored Wootz-like structures for aerospace applications. In 2018, a leaked internal memo from an Indian military research agency described a carbon-dense alloy based on pre-colonial metallurgy with anomalous fatigue resistance. No follow-up publication appeared. Some believe the data is now classified. If true, Wootz may have held the key not only to superior swords, but to technologies far beyond its time, from surgical tools to spaceflight components. Satellite imaging of ancient smelting sites in southern India shows extensive slag fields and furnace mounds that have yet to be excavated. These locations are now under restricted control, allegedly for archaeological protection. But no public research has been conducted there in over a decade. If Wootz steel represents not just lost craftsmanship, but a forgotten science of nanostructure manipulation, achieved without microscopes or formulas, then its disappearance is more than a cultural loss. It is a technological regression, a reminder that sometimes the future is buried in the past. The Libyan Desert Glass. In 1932, during an expedition across the Great Sand Sea bordering western Egypt and Libya, British geologist Patrick Clayton stumbled upon scattered shards of pale yellow-green glass shimmering beneath the sun. The fragments were oddly shaped, razor-sharp, and unnaturally smooth, unlike anything formed by wind or erosion. Over the following years, explorers and geologists would discover over 3,000 square miles of this strange material, now known as Libyan Desert Glass. But nearly a century later, scientists still cannot agree on how it was created, or what cataclysmic event could have produced temperatures high enough to form it. Libyan Desert Glass is almost pure silica, over 98%, and displays a clarity and consistency rivaling the highest grade optical glass used in precision instruments. To melt quartz sand into glass, temperatures must exceed 3,100 degrees Fahrenheit. No volcano exists in the region. There are no signs of lava flows, magma tubes, or geothermal vents. Even more puzzling, there is no impact crater nearby, ruling out a traditional meteor strike as the source. The glass appears to have formed from an intense but shallow thermal event, possibly an aerial burst or explosion that vaporized everything in its path without leaving a scar in the earth. In 1996, NASA scientists began studying the glass as an analog for lunar surface processes. One theory suggested that the glass could have been formed by a comet airburst, similar to the 1908 Tunguska event, where a cosmic body detonates in the atmosphere, generating immense heat without touching the ground. But even this hypothesis fails to explain the uniformity of the glass or the presence of microbubbles and rare high-pressure minerals like cristobalite and le chatelierite, which require both intense heat and compression. What deepens the mystery is the context in which this glass has appeared historically. A scarab carved from Libyan Desert Glass was discovered in the breastplate of Pharaoh Tutankhamun's burial mask, suggesting that ancient Egyptians valued the material not only for its beauty, but for its supposed mystical or technological properties. The carving techniques used on the scarab imply a knowledge of the material's hardness and fracture patterns, knowledge that would have required experimentation and perhaps even quarrying. Attempts to replicate the glass in laboratory conditions have been marginally successful, but require tightly controlled high-temperature plasma generators and synthetic atmospheric conditions. No known natural process on Earth, except perhaps nuclear detonation, matches the energy and uniformity of the event that formed this glass. And yet, nuclear testing was more than 3,000 years in the future. In 2007, a classified report from an international geophysical survey mentioned anomalous magnetite levels and neutron activation patterns in samples of Libyan Desert Glass, indicators consistent with exposure to high-energy particle bursts. That report was never published in full, and the raw data remains inaccessible. In recent years, the area around the densest concentrations of Libyan Desert Glass has been placed under military control by local authorities, citing concerns over unauthorized artifact removal. Satellite surveillance shows that excavation activity has continued in isolated sectors, conducted by teams unaffiliated with any known academic institutions. Independent researchers attempting to access the region have been turned away or detained. If Libyan Desert Glass is the residue of an unknown cosmic event, or worse, the technological remnant of an ancient weapon or energy experiment, then it stands as physical evidence that Earth has experienced forces beyond current human understanding, forces that may not have come from this planet. Or if they did, forces we are no longer allowed to explore, the Incan shadow resistant. In 1936, while surveying temple ruins near the remote Peruvian site of Choqquequirao, a team of archaeologists led by Dr. Harold Ferguson noticed something odd beneath layers of moss and time-worn debris. The inner walls of a sun shrine, exposed to harsh high-altitude sunlight and seasonal rains for centuries, still bore faint but vivid traces of crimson, ochre, and blue. Unlike typical mineral pigments, which fade or flake over time, these colors had bonded seamlessly with the stone, their hues almost untouched. Initial samples sent to Cambridge for analysis stunned researchers. The paint had not degraded. It had resisted not just weather and moisture, but even ultraviolet radiation. The ruins were coated in a compound that modern materials science could neither replicate nor fully explain. The chemical structure of the pigment, later named Andean Compound Red 5, was unlike any known paint or dye from pre-Columbian America. It consisted of organic and inorganic binders suspended in a silica-based matrix, but with a twist. Embedded in the pigment were microscopic particles of biogenic silica, glass-like structures derived from plant ash, that diffused incoming sunlight in a way that prevented color degradation. Essentially, the paint neutralized UV exposure. Under electron microscopes, these particles resembled nanoprisms, precisely spaced as if engineered. Further complicating the mystery, the paint also showed resistance to microbial growth. Fungal cultures could not penetrate the film even under high humidity conditions. The binder appeared to contain enzymes or alkaloids derived from local flora, possibly processed through methods lost to history. Indigenous oral tradition hinted at sacred sun plants, used by Incan priests to create protective coverings for temples. But no such recipe exists in preserved records or codices. The preservation effect of this coating remains unreplicated by any modern formulation without synthetic polymers. In 1981, a joint project between a Swiss paint manufacturer and Peruvian cultural authorities, attempted to recreate the pigment using only natural substances found in the region. The project ended in failure after 2 years. Shortly afterward, several samples of the original paint layers stored in Lima's National Archive were reported missing. An internal investigation concluded administrative error, but the case was quietly closed. The lead researcher resigned and left the country. Satellite imaging in 2010 revealed other Andean structures with similar residual coloration, particularly in sites not open to the public, such as Pumaquiri and parts of the Vilcabamba corridor. These zones have since been sealed off for cultural conservation, with no further access granted to independent researchers. The Peruvian Ministry of Culture has denied requests to release spectral imaging data or pigment samples from these locations. Why would a civilization with no access to synthetic polymers or modern optics create a paint capable of outlasting even the most advanced modern coatings? Some believe the Incas inherited knowledge from earlier cultures, perhaps even from pre-flood civilizations, that had mastered nanostructured materials. Others point to the solar cults of the Andes, suggesting the paint was part of a broader system of light manipulation and sacred geometry. A few fringe researchers even speculate on energetic properties, theorizing the pigment acted as a solar capacitor, though no mechanism has ever been demonstrated. In recent years, rumors have surfaced of military-grade paint formulations being developed based on recovered data from Choqquequirao. These coatings are said to resist thermal imaging and UV-based detection systems. None have been acknowledged publicly. Yet the enduring color on those ancient stones remains, silent, unyielding, and untouched by time. If the Incas truly created a paint that resists sunlight, moisture, mold, and decay, without modern chemistry, then we are no longer looking at primitive artisanship. We are staring at the ghost of a science that should not have existed, the Chinese flexible glass. In 14 CE, during the reign of Emperor Wang Mang of the Qin dynasty, a craftsman appeared at court bearing a gift so strange it was recorded in multiple imperial annals. He presented a drinking cup made from what he claimed was flexible glass, a material that did not shatter when dropped, but instead dented and could be reshaped with a small hammer. The emperor was intrigued and asked how it was made. When the artisan refused to reveal his process, Wang Mang ordered his execution and had the workshop destroyed. That decision erased the only known attempt to introduce flexible glass into the ancient world, and left behind a mystery that has haunted material scientists ever since. The story appears in several historical sources, including the Book of Later Han and writings from the Eastern Jin dynasty centuries later. Some historians dismissed it as apocryphal, but in 2012, a curious link emerged when modern tech companies announced the development of ultra-thin, flexible glass for touchscreens and solar cells. The material, known today as willow glass or gorilla glass, shares properties eerily similar to the artifact described in Han records. Could the ancient Chinese artisan have discovered a form of high-tensile, low-micron glass without any industrial technology? While no surviving sample of the original flexible glass has ever been recovered, Chinese archaeological digs in Luoyang and Chang'an have unearthed fragments of early glass that defy classification. Some of these pieces contain traces of rare alkali metals and boron, elements used today to produce lab-grade borosilicate glass. A 1999 study published by the Chinese Academy of Sciences detailed a shard containing high levels of lithium silicate, which reduces brittleness and increases heat resistance. But the paper was withdrawn shortly after publication and never translated into English. What makes the story more troubling is how consistently any trace of this material vanishes from historical records. Unlike bronze or jade, glass in ancient China was rare and often considered inferior to porcelain. Yet during the early Han period, court documents briefly reference a clear stone that bends but does not break. After Wang Mang's purge, these references disappear. It's as if the discovery was not just silenced, it was systematically erased. In 2008, an anonymous white paper circulated within the Chinese materials engineering community mentioned an ancient silicate anomaly recovered from a closed tomb site near modern-day Suzhou. The document claimed the sample could bend up to 12 degrees without cracking and retain structural memory. Attempts to reproduce the material failed, and the sample itself was never revealed. To date, no institution has claimed authorship of the paper, and no peer-reviewed analysis has followed. Flexible glass in the modern world requires precise doping agents, slow thermal annealing, and clean room production. If such a substance existed over 2,000 years ago, it implies not just accidental discovery, but an understanding of heat treatment, chemical balance, and perhaps even atomic structure manipulation far beyond the known capabilities of the time. As recently as 2020, restricted excavation reports from the Henan Provincial Archaeological Institute listed an unclassified vitrified object with trace rare earths in a Han Dynasty burial site. No photos were released. The entry was removed from subsequent publications. If the story of the flexible glass is true, and if even fragments of such a substance remain, then it represents a technological leap centuries ahead of its time, not only for its physical properties, but for what its suppression reveals about knowledge, power, and fear. The question is no longer whether flexible glass existed in ancient China. The question is, who decided the world was not ready for it? Conclusion: these ancient materials reveal a disturbing pattern, one that transcends borders, cultures, and centuries. From the volcanic harbors of Rome to the high temples of Peru, from the smelting forges of India to the desert glass plains of North Africa, each case points to a truth long ignored. Our ancestors possessed knowledge of material science that defies modern explanation. These are not isolated anomalies. They are signs of a model, a hidden architecture of forgotten innovation. This model is marked by systematic erasure. In every story, someone silenced the source. From imperial execution in Han China to colonial suppression in India, from sealed museum archives in Europe to restricted excavation zones in the Middle East, the pattern is chillingly consistent. When these discoveries surface, they are first studied, then hidden. The results are either redacted, reclassified, or simply vanish. Academic careers end. Research is redirected. Access is denied. It's as if there exists an unspoken consensus that some materials, and the truths they imply, are too dangerous to share, and the cost of this suppression is immeasurable. These materials weren't just marvels of engineering. They carried possibilities that could have transformed medicine, construction, optics, energy, and aerospace, concrete that repairs itself, glass that bends without breaking, paints that defy time, and ultraviolet light. Each represents a future we never inherited, a road not taken, a technology buried not because it was misunderstood, but because it was too advanced for its time, or too disruptive for those in power. This is not merely about lost knowledge. It is about what was taken from humanity. Entire branches of science amputated from the collective memory. Every crushed tablet, every vanished lab note, every sealed vault tells the same story. That we are not the first to walk this road, but we might be the first to pretend we paved it ourselves. And the suppression continues. Excavation sites are militarized, artifacts are reclassified, samples disappear. In some cases, the most extraordinary materials are labeled unremarkable simply to avoid public scrutiny. But the fragments persist. A glowing ingot in a shipwreck, a painted wall that will not fade, a scarab carved from the glass of a vanished explosion. Each is a silent witness to something we are no longer allowed to ask. Because the real danger isn't that we don't know how these materials were made. The real danger is that someone does.